Today we study the second one of the three big theorems in semigroup theory. The first one was the Hille-Yosida, and this tells us when an operator A is a generator of a semigroup T. The Lummer-Phillips theorem could be seen like a special case. It deals with contraction semigroups, and I will talk about in a second what that is. And then what I consider the third big theorem is a perturbation result, which we study then next week. So if we go back, let's go back to the Hille-Yoshida for a second. Here it is, right? So for A to be a generator, we in the end have to satisfy this condition down here. We have to have a resolvent estimate for R lambda A to the n, and this for any n. And now this condition is relatively hard to check in most cases, because we have to do it for all n. So the Lummer-Phillips theorem makes it a bit easier, and we can get away with n is 1, right? And if you have n is 1, you only need to check one resolvent estimate, which of course is much easier to do. So here we go. So if m is equal to 1, m is this m gamma was the coefficient in the Hille-Yoshida estimate, and if this is 1, then we can get away with just one resolvent estimate. R lambda A be bounded by 1 divided by lambda minus omega, where of course lambda is bigger than omega and real, because by iteration then we can get the same result for the power of n. And now this observation we use here in the corollary to the Hille-Yoshida. So the operator is generator of a strongly continuous semigroup with a growth bound e to the omega t. Alright, so here this was where the m was, so the m gamma is equal to 1. If dA is dense, A is closed like usual, and then we have one resolvent estimate and no longer n resolvent estimates. Now the Lummer-Phillips theorem takes it a little bit further, and this case is so important that it gets a different name. So we call a semigroup a quasi-contraction semigroup if this constant in the estimate is equal to 1. And we call this a contraction if the omega is 0. So if the estimate t of t is less or equal 1. No time dependence there. So quasi-contraction, this constant m is 1. Contraction, we also have that the growth bound is 0. And then we can have Lummer-Phillips. So let A be a linear operator on a Hilbert space. So now we are also Hilbert. Assume dA is dense, and for all x in dA, the real part of xax is bounded by omega xx for some positive omega larger or equal 0. Now again, this is a condition easy to be checked. You just need to compute the scalar product of x with ax, take the real part, and see if you can estimate it. And then third, for one lambda 0, we need a resolvent in detail, so there must be a lambda 0 larger than omega, so that a minus lambda 0 I is onto. If we have a resolvent, then it will be onto automatically. And then A generates a quasi-contraction semigroup with the estimate e to the at is bounded by the growth bound e to the omega t. So for the proof, we will simply use the Hille-Yoshida theorem, or actually the corollary, which I just had before. So let's assume lambda is bigger than omega, and then we estimate, so we start here, this expression, the inner product of x with lambda I minus ax, and then we can use Cauchy-Schwarz here on the left, get something bigger if we use the norms of these two terms. And then we can also estimate this, since we have minus xax will be larger or equal minus omega xx from item number 2 upstairs, so then we get this estimate here. Now if lambda is bigger than omega, then lambda minus omega is positive, and so this is bounded away from 0. It's bounded below away from 0, and we have seen earlier in corollary 734 that the resolvent then exists. But even more so, we also see that then the resolvent here can be estimated by 1 over lambda minus omega. So that was the one condition of this corollary we had before. Now we take such a lambda 0, where we just did the estimate, and the resolvent exists, so the range of a minus lambda 0 I is the entire thing of x. So a minus lambda, here should be 0, I is closed, and this also means a is closed operator. And so now we can apply the corollary 851, which I just had at the page before, and we get a strongly continuous semigroup of quasi-contractions. T of t bounded by e to the omega t. Let's do an example. So, assume A is self-adjoint on a Hilbert space H with dense domain D of A. And now we do the spectral representation. So we assume lambda I denote the real eigenvalues. And we assume that omega, which will be the growth bound, is bigger than the maximum of all the real parts of all the lambdas, where lambda is in the spectrum. So it really needs to be bigger than everything of the spectrum. In this case, we can have a continuous spectrum, residual spectrum, all that kind of stuff. And omega needs to be bigger than the real part of all of these. The phi I denote the orthonormal basis of eigenvectors. And then in Luma-Phillips, we need this estimate for xax. Let me just go back up. So here you see in item 2, there we need the estimate for the real part of xax. Let's do that. So then xax spectral representation, we have the sum I is 1 to infinity, lambda I x phi I, and the omega is bigger than all the lambda i's, so all the real parts. So then this is less or equal omega times the sum of this, and the sum is just the norm in the Hilbert space, squared. So then for lambda 0 bigger than omega, the resolvent exists, which means 1 minus lambda 0 I is onto. The note's getting worse. What's happening here? Lambda 0 I minus a is onto. And then by the Luma-Phillips theorem, A generates a quasi-contraction semigroup. Note here the spectral bound omega is essential. And this is what we then will be worried about in applications. It's often the question, what is the omega, what is the growth bound here? Second example is my little box, where I look at one derivative, d by dx, on L2, 0, 1, and I just assume one condition which says u at 1 is equal to 0 on one of the boundaries. We put the boundary condition in the domain, so right here, so then I call the domain of A all functions which are weakly differentiable, and at the 1.1 this function is equal to 0. The domain is dense in L2, since H1 is dense in L2, and functions in L2 are only defined up to a set of non-zero measure 0, so the condition at one of the boundary points is not relevant for representations in L2. Now we compute the spectrum of A by really solving the resolvent equation. So the resolvent equation here is A minus lambda I u is equal to phi. Given phi, find u. And if we use A, the definition, we can write this as a differential equation. U dot is lambda u plus phi. And this is just a linear ODE with one side condition, u at 1 is 0, which can be solved for any lambda in C. Hence, A minus lambda inverse exists for all lambda in C. Okay, now you might get a little hiccup because at some point I've shown that the spectrum is never empty. And here I show the spectrum is empty. Well, the result spectrum never empty is only for bounded operators. Now here A is an unbounded operator, and this is an example where the spectrum in fact is empty. Okay, so then in this case, since every lambda has a resolvent, we can choose a growth rate to be 0. And then we apply Luma-Phillips, and we need still the estimate for A, for U, AU. So A was a derivative, so then this is this integral. We can do integrations. And with the u1 term which would arise is equal to 0 from the boundary condition, but we keep the u0 term with a minus sign. And so that's the right sign, so let's equal 0, so here we can choose omega is 0. And then this whole thing generates a contraction semigroup T, which is bounded by 1.